Hi, and welcome to day 6.5. We're talking about scientific notation and comparing exponential and linear functions today. Scientific notation is probably something that you've seen before, maybe in 8th grade or 7th grade, and it's used in science, as the name might suggest, to write very large and very small values more efficiently, because these numbers tend to have a lot of decimal places. So this allows us to write those numbers with just writing the important parts of that number without writing a lot of zeros or other numbers. So what do we need to know about scientific notation? This first number, which we're going to call A, needs to be between 1 and 10. So really it just needs to be one number before the decimal place. So it's going to be a number and then a decimal place, and then we can have a whole bunch of other numbers, right? But it has to be one number before the decimal place. So that can be a 1, a 2, all the way up to a 9. But if it's a 10, we're going to have to make that smaller, so it's more like a 1. That number can be positive or negative. And that's what we need to know for the first number. All right. The second number, the second part of this is the B value, the exponent. That can be positive or negative as well, right? But it's going to be a positive number for very, very large numbers and a negative number for very, very small numbers, right? Because a positive exponent means we're multiplying by 10 that many times. And a negative exponent would mean that we're dividing by 10 that many times. So that's how we make small numbers. So here are some examples of numbers written in scientific notation. So if we take a large number like 47,300, we would write that as 4.73. So we're moving that decimal point from here after the number to between the 4 and the 7. Again, keeping that one digit to the left of the decimal place and moving that decimal over. And then we were saying, how many times are we moving that decimal over? 4 times, right? We can go 1, 2, 3, 4. And that's where we're going to get this number here. We know it's a big number, so it has to be a positive exponent. For a small number example here, this is 0.0037. So again, we have to move that decimal point so that it's between the 3 and the 7. We want one non-zero digit to the left of that decimal. So we're going to go 1, 2, 3, move it 3 times to put it between the 3 and the 7. And that is reflected in our exponent, right? We moved it the other direction 3 times. So it's going to be -3 as our exponent. So again, that means we're dividing 3.7 by 10 3 times to get that 0.0037 number. So I just kind of talked a little bit about how to convert from standard form to scientific notation, but here are your rules to read through and look at whenever you're doing a scientific notation problem. You have to count how many times the decimal needs to move to make the A number between 1 and 10, right? So that's getting that one digit to the left of the decimal. Write that new A value, then you're going to write times. This is the only time we use X to mean times. Okay, so that little cross, 10. And then we're going to figure out what our exponent is. So our exponent B is the number of times you moved the decimal. Okay, and it's going to be positive for a big number, right? And it's going to be negative for a small number. So that's how you can remember if it's positive or negative. And you can always look back at these examples in your notes if you have any questions. So here are a couple of examples on how to do this. So remember, if we have a number like in number 1, which is 140,000, we remember that even if we don't see that decimal point, it's really living right there at the end of this number. We have to move this decimal so that it's between the 1 and the 4, right? We want one decimal, we want one number to the left of the decimal, and then as many as we want to the right. So how many times do we have to move this decimal? We're going to move it. So we're going to get 1.4, right? We know that, but now we have to figure out how many times we're moving it. So I'm not going to write my exponent yet. We have to count. 1, 2, 3, 4, 5. So we had to move this 5 times, and this is a big number, so I'm going to leave it as a positive 5. In example 2, here we're doing the same thing, but now we have a small number. So I have to move this decimal, so it's between the 6 and the 7. So how many times do I have to move that decimal? 1, 2, 3, 4, 5 as well, okay? So 5 times to put that decimal between the 6 and the 7. So we're going to write 6.7 times 10 to the, well, the only difference here is this is a very small number, so we're going to make this a -5. So those are two great examples to look back at whenever you have questions on which way to move your decimal point, or which way, or how to write your exponent. Okay, remember you can always pause these notes and go back at any time. The next section here is about how to convert from scientific notation to standard form. So standard form, we've heard that term before, but right now it just means a regular number. So that's all we mean when we say standard form, right? If we're talking about scientific notation, what is that actual number? So we're going to move the decimal as many times as the exponent. We're going to move it to the right if it's a positive exponent, and we're going to move it to the left if it's a negative exponent. And then we take away that times 10 to the, right? We just take that whole part away. So we're just going to take that that first number. So I'm looking ahead at our first example here. We're going to take that first number and just write that, move the decimal, and write our answer. So here's how I would do this one. So I'm just going to start with my 6.5, right? I'm looking here, but I'm not writing that part. I'm going to say, okay, this 3 exponent means it's going to be a bigger number, and I have to move the decimal 3 times. So I'm going to start where my decimal is right here, and we're going to go 1, 2, 3, okay? So there's where my decimal is, but you see these spaces? I just made a whole bunch of spaces here that we need to fill in with zeros. So my last step is just going to be to rewrite this number, 6,500, as one regular old number. So remember, standard form, regular number. We shouldn't see any x's. We shouldn't see any exponents. It's just a number. All right, so this next number here is 1.2 times 10 to the -7. Okay, so this is telling me it's a very small number. So I'm going to start with my 1.2 kind of over to the right, because I know I have to move my decimals to the left. I need some room for that, okay? So here's my negative exponent. We're going to move to the left 7 times. So including from to the right of the 1 to the left of the 1, that's 1, 2, 3, 4, 5, 6, 7. Then I'm going to fill in 1, 2, 3, 4. Okay, so I moved my decimal 7 times, and I had to add 6 zeros there, right? So I have 0.1, 2, 3, 4, 5, 6, and then our 1 and our 2. So here is our actual number. We had to move our decimal 7 times, and that's only 7. What if this was a -20, right? We wouldn't want to write that number with 20 zeros or 19 zeros in front of it. It would be a lot to read. So that's why we use exponential form. All right, let's do a little practice here. This is just comparing numbers. So this one's saying, which is bigger, 10 to the 5th or 10 to the 4th? Right, 10 to the 5th is multiplied by 10 5 times versus multiplied by 10 4 times, so that's going to be bigger. Now we're talking about negative exponents, so 10 to the -5th or 10 to the -6th, right? Remember, this is dividing, which is going to keep making that 10 smaller. So I want the one that's bigger is going to be the one that divides fewer times. And this is exponent review. It's not always tens. That's scientific notation. But for any number, right, 4 to the 9th is always going to be bigger than 4 to the 8th. Okay? And now we're going to put these numbers in order from least to greatest. So in order to do that, we're going to convert these either all to standard form or all to scientific notation. I would prefer to compare them in scientific notation because I think that makes it easy to do. So here's what we're going to do. We're going to write this first one in scientific notation. So that means I'm going to move this decimal point. So it's going to go between the 2 and the 1. So we're going to get 2.19. We know that. And now we just have to see how many times I have to move this. So we're going to go 1, 2, 3, 4, 5, 6, 7. 7 times. And I'm going to do the same thing here. This is going to be 2.32. Right, this is going to be a bigger number as well. 1, 2, 3, 4. We had to move that one 4 times. So now all we really have to look at here is which has the bigger exponent. So of all these numbers, 1, 2, 3, 4, right? This one's got the biggest exponent. So this is going to be the largest number. Okay. And then I'm going to look at my two that have 10 to the 5th, right? I have two of them that have the same power of 10. So now I'm going to look at the first number. So now I'm going to say 2.32 is bigger than 2.19. So this one's got to be bigger than this one, leaving our number that's 10 to the 4th, right? That's the smallest exponent. That has to be our smallest. Oh, except this said from least to greatest. So let's try that again. We'll just reverse that order. Least to greatest. So here's our least. Then it was this guy, 2.19, then 2.32, and then our 10 to the 7th, right? But I'm looking at those exponents first, and if the exponents are the same, then I'm comparing the numbers out front, that a value. And here's just a little bit more comparison. Again, same idea, right? We're going to look at the exponent first. So I don't care about the 3.7 and the 8.5, right? For this one, I'm looking here. 10 to the 5th is always going to be bigger than 10 to the 4th in scientific notation. 10 to the 4th is always going to be bigger than 10 to the 3rd. So now we have 10 to the 4th, 10 to the 4th. Now I have to look at the 9.5 is bigger than 3.7. Okay. The next one, number 8 here, I'm looking again at the exponents. And technically, 10 to the negative 3rd, right? Negative 3 is bigger than 10 to the negative 4th. And then finally, our last one here, 10 to the negative 1 or 10 to the 0. 0 is bigger than negative 1. So finally, we have one that goes the other direction. All right. So the only time I'm comparing that front number is when the exponents are the same. Okay. That's the only time I'm comparing that front number. Okay, let's move on to our next set of notes, which is comparing linear and exponential functions. So an exponential function is a function where the exponent changes. So that means the exponent is a variable, right? It's saying the number of times I'm multiplying by the base is going to change. A linear function is a function with a constant rate of change. We've talked about linear functions last semester. So the key word in linear is line. Okay. So that means the variable is being multiplied by a number. We know that because these are in the form y equals mx plus b. Oop, that does not look like a plus. There we go. So there's our variable being multiplied by the slope. So our exponential parent function looks like this. Y equals a times b to the x. And our linear parent function is our old friend, y equals mx plus b. So your exponential equation has a constant ratio. Ratio means we're multiplying by the same amount every time. And a linear equation has a constant difference, which means we're adding the same value every time, right? So this is one that we've seen before. We have seen linear equations. We should be fairly familiar with those. But let's see what that looks like in a table, right? So here's my linear table. 0, 0, 1, 2, 2, 4, 3, 6, 4, 8, 5, 10. Right, so if we look at our outputs, here's our outputs. Y is our outputs. And we're saying, how is this changing? Well, 0 to 2, we would say plus 2, 2 to 4, plus 2 again. And we're looking for this pattern that's the same every time. So we're adding 2 every time. That's the constant in constant rate of change, right? And it's adding. So that's how we know it's linear. So if this is adding the same amount, that's how we know it's linear. Okay, if I look back over to my exponential one, this is our new one. We haven't seen an exponential function before. Okay, so now I look at my outputs. So again, y is still outputs. That hasn't changed. But we're looking and we see 1, 2, 4, 8, 16, 32. Well, if I try to go, okay, this is adding 1, but then this one's adding 2, and this one's adding 4, well, something's not right here. It's not the same amount. So we have to go back to the drawing board, so to speak, right? We have to say that's not the right pattern. So then we say, okay, am I multiplying by something? 1 times 2, or 1 times what is 2? So if I multiply by 2, I would get 2. Does this pattern continue? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32, right? So we can kind of see that pattern. It's the same every time, and it's multiplying. That's how we know that it's exponential. Okay? If neither of these are true, if we're not multiplying by one number or adding one number, then it's neither. Okay, so our exponential, what does it look like? Well, our exponential graphs are curved. All right, they're curved. They are growing or decreasing exponentially, and they're approaching 0 on one side. So you can see how this one's approaching 0 on the left, and this one's approaching 0 on the right. Okay, our linear equations, right? We just said linear means it's a line. You graphed a whole bunch of these in semester 1. It's a line. That's it. All lines are straight. It's a line. If it's a line, it's linear. If it's not a line, it might be exponential. It might not be. All right, let's do some quick examples here. We're going to practice what we know. So let's take a look at number 1. We're looking for patterns. When I see 1, 3, 9, 27, 81, see how these numbers are getting really big really quick? Chances are that means it's exponential. So if I multiply by 3, I'm going to get to the next number in this pattern. So this one is exponential. All right, if I look at number 2, number 2 is a line. That's how I know it's linear, right? It is a line. Linear, line, it's right there in that word. All right, let's look at number 3 is our next table. So 0, 3, 6, 9, 12. See how this one feels like counting by 3s? That's because we are. If we add 3 every time, 6 plus 3 is 9, 9 plus 3 is 12. We are adding 3 every time, so this one is linear. Okay, our next one here, it's a curve, right? So we know it's not linear, okay? But it's not approaching 0, right? Our exponential curves either look like this or they look like this, but they're approaching 0 on one side. This one is neither of those things. So it's not exponential, it's not linear, it is neither. Okay, and let's move on to our last 2 here. So let's look at this one. So we got 0, 1, 2, 3. Oh, so I know this one looks like it's adding, right? Because I wouldn't multiply anything by 0 to get 1. But we're adding 1, we're adding 1. Oh, but look, 3 to 6, we're adding 3. So this one's not linear. There's nothing I can multiply by that's going to work here. So this one is also a neither. So we have to look and make sure that pattern works for all of the table, not just some of it. And finally here we have a curve. We have it approaching 0 on one side, right? See, it's approaching 0 on the right here. It's definitely not linear. This is an exponential graph. So this one is exponential. And that's your notes for today.